In this video, we're going to talk about evaluating definite integrals, and we're going to be doing it using something called the Fundamental Theorem of Calculus Part 2. So in a previous video, we talked about using geometry to sort of think about evaluating definite integrals. Remember that definite integrals represent the area under a curve over some interval. And as you might guess, the fundamental theorem of calculus is kind of important. Fundamental, you might say, to the study of calculus. So this is part 2. They're not really sequential necessarily, but the one that relates to evaluating definite integrals is part 2, and it's this theorem here written in red, which is that if you have a continuous function on a closed interval, then if you want to evaluate the definite integral, so remember this definite integral from a to b of f of x dx, that sort of represents the area under this curve, the signed area under this curve on this interval. And what this theorem says is that basically all you have to do is evaluate an antiderivative, any antiderivative. Because in general, like if I'm taking capital F of b minus capital F of a, whatever the constant of integration is going to cancel out when I do this subtraction. So in general, we always take the antiderivative with constant 0, just because we can use any one we want, and that's the one that makes the mathematics the easiest. So this is super valuable, important, time-saving, however you want to classify it. Because remember that the definition of this is it's a limit of Riemann sums. That's not exactly like clean and easy to work with. So the fact that instead of using the limit of Riemann sums, you can just evaluate an antiderivative is incredible. And the proof of this is not super hard. We're not going to go into it in this video, but essentially it just uses the mean value theorem and a little bit of slick algebra. So one other quick thing before we work some problems is some new notation. So we're going to be using this vertical bar notation, which is pretty common. The vertical bar after a function usually means to evaluate the function. So here we're evaluating at b and subtracting what we get when we evaluate it at a. So rewriting this up here in red, the definite integral is an antiderivative evaluated at b and then subtract what you get when you evaluate at a. So if you see this vertical bar notation, that's what it means. Okay, so let's just do a couple of these. So let's say we want to evaluate the definite integral from 1 to 2 of x to the negative 2/3 plus 2 over x dx. So then the first step is to take the antiderivative of the function on the inside. So using the power rule for integrals, we can add 1 to this and get x to the 1/3. And then we divide by the new exponent. Dividing by 1/3 is the same as multiplying by 3. So that's the antiderivative for this piece. Here we can factor out the 2. Antiderivative for 1 over x is natural log of absolute value of x. And we're going to be evaluating this antiderivative function from 1 to 2. And again, I'm just going to automatically assume that my constant here, I don't have to put plus c because I'm going to be evaluating at 2 and then subtracting at 1, so those c's are going to cancel. So I'm just choosing the antiderivative where I'm adding 0 as the constant, and that's perfectly fine. So then this says 3 times 2 to the 1/3, right, plus 2 times the natural log of the absolute value of 2. We have this. Then we're going to subtract what we get when we do 3 times 1 to the 1/3 plus 2 times the natural log of the absolute value of 1. So then we just need to clean this up a little bit. So this is going to be 3 times the cube root of 2 plus 2 times the natural log of 2, because of course the absolute value of 2 is just 2, so I can evaluate those absolute value symbols. And then I'll get minus 3. And then natural log of 1 is equal to 0, so this term is just going to disappear. Cube root of 1 is just 1, so I get this. And you could put the 3's together and like try and factor a 3 out, but honestly, this is an okay answer. So again, what the fundamental theorem of calculus says is to evaluate a definite integral, you basically just take an antiderivative and evaluate it at the endpoints and take their difference. So let's try one more. Let's say we want to take the antiderivative or evaluate the definite integral from 0 to pi/4 of secant 3x times tangent 3x dx. So you may want to pause and try to work this one on your own. Okay, if you're back or if you chose not to do that, that's fine. So we want to take the antiderivative. Antiderivative of secant tangent is secant right? So secant 3x, because the derivative of secant is secant tangent, except this is what I would call a baby chain rule problem, where the inside of our composite function is linear. So when you take the derivative of this, a 3 would pop out, which means that you need to introduce a 1/3 to sort of kill off that 3. So this is the antiderivative, and I'm going to be evaluating it from at 0 and pi force, right? So then this is going to be 1/3 secant 3 times pi force minus 1/3 secant 3 times 0, right? I'm just plugging in for x in both of these places, taking their difference. So then this is 1/3 secant of 3 pi force. Secant 3 pi force is negative square root 2 minus 1/3 secant of 0. Secant of 0 is 1, because cosine of 0 is also 1, right? So then this is going to be negative root 2 over 3 minus 1 over 3, or negative root 2 minus 1 all over 3. So this is the value of the definite integral. So another sort of wrinkle on these problems that's essentially the same is you might, instead of just be given a problem that asks you to find the definite integral or to evaluate it, you might be asked find the area under the curve. So this is very similar to the previous two, except it also requires the extra sort of step that if you want the area under the curve, that's what the definite integral gives you. So here, the first thing I have to do is set up the definite integral and say, oh, well, that area under the curve, that's given by take the definite integral over the appropriate interval. So now, after this step is complete, it's exactly the same as the previous ones. So I take an antiderivative. Again, you may want to pause and try to work this one out yourself. I take the antiderivative of e to the x, I get e to the x. I take the antiderivative of 2x, I get x squared. I'm evaluating that from 1 to 3. So this is e cubed plus 3 squared, when I plug in 3, minus e to the first plus 1 squared. So this is e cubed plus 9 minus e minus 1, right, because I distribute my negative here, or e cubed minus e plus 8, right, because these are similar terms. And you can't really clean up these e's, right, like e's to the different powers don't combine very well, so this is a perfectly fine final answer. So this is certainly an example where you would not be able to use geometry to find the area under the curve, right? Instead, you'll have to sort of use your knowledge of antiderivatives to sort of evaluate this area using the fundamental theorem of calculus. So to wrap up this video, I just want to make a quick comment. So far we've seen a couple types of notation, this integral symbol, right? And this integral symbol that goes with a differential, dx, at the end. And we've seen this with no upper and lower limit, and now we've seen this with that does have an upper and lower limit. So with no upper and lower limit, this is called an indefinite integral, right? So this means I'm not fixing an interval at all. And this notation means just take an antiderivative. This notation is asking about the area under the curve, right? And it is a definite integral. So indefinite means no upper and lower limits. Definite means it does have upper and lower limits. And when you evaluate this, what you should get is a function, right? So you're going to get some function that represents an antiderivative here. But when you evaluate this, your answer should not be a function, but should be a number, right? Specifically, it's going to be a number in square units, basically, where you're evaluating, you know, the area under whatever this curve is. So this is a function when you are done. This is a number when you are done. And often when students are first getting the hang of antiderivatives, they wonder when you're supposed to put plus c and when you aren't. And this is the sort of dividing line. If you've got an indefinite integral, that always gets a plus c. If you have a definite integral, that never gets a plus c, right? Because you should have a number, not number plus c, right? If you end up with function, you should have plus c, but if you end up with a number, you don't want plus c. So this is the fundamental theorem of calculus part 2 and how it is used to evaluate definite integrals.